Okay, let's try an example. Let's try setting this equation to 0. Let's try setting 2x squared plus, I don't know, 24x plus 8 to 0. Okay, so you might say, well, wait a second, we have this method we invented, we call it completing the square. It works for x squared plus bx. We don't have x squared plus bx. We have 2x squared plus bx. What can we do? Well, there's a nice way around that. What I could do is, hey, I have this on the left equal to this on the right. These two things are equal. That means this thing is this thing on the right, so if I do something to this side, like multiply by a half, and do something to this side, like multiply by a half, both sides are still going to be equal. So, this may look like cheating. 1/2 of 0 on the right. Well, when I distribute this 1/2, I get this. So it may look like I just changed the problem, but what I had here was this and 0, and what I have here is this and 0 over 2. And since 0 over 2 just happens to be 0, well, there's nothing I can do. It's still going to be 0. So, now what we have to do is compute b over 2, which b is 12, so this is 6, and b over 2 squared, which is 36. So I now get x squared plus 12x plus 36 minus 36 plus 4 equals 0, because we're adding 0 here. And once we group, we always get x plus b over 2 squared. So what do I have? I have x plus 6 squared, and now here I have minus 32, or if I move it to the right, I'll have a plus 32 on the right. So what can I do? Well, I just use my rule for radicals and get plus or minus root 32, or x is equal to minus 6 plus or minus root 32. Now if I wanted to, and this is the right answer, but if I wanted to, I could simplify this a little further, because 32 is 16 times 2. So this would be root 16 times root 2, because the square root of a times b is the square root of a times the square root of b, at least for positive a and b. And we get plus or minus 4 root 2. And that completes the problem.